Okay, so in the last video we talked about what happens when what happens in terms of delta H of solution, and we said that it was dependent on the delta H lattice energy, which is really a measure of the strength of the bonds inside of a particular crystal. And then we add that to the delta H of solution, which is mostly dependent on the strength of the bonds formed between the solvent and the solute. Okay, but what we came to the conclusion was that delta H of solution is generally pretty close to zero, or more like really more often than that, it's slightly positive. But if delta H solution is slightly positive or close to zero, then why does this process happen at all? It should be the question. Because delta H needs to be negative. So again, just getting back to these core principles here that negative delta H is favorable. That's all. I'm building on these very basic things, but we're doing a lot with them. Delta H needs to be negative for a reaction to be favorable. And I use the word reaction interchangeably with things that are generally considered physical properties like dissolving things. I'm talking about just the process. But okay, so delta H needs to be negative for a reaction to be favorable, but here we have delta H of solution that's zero, or slightly positive, which is even worse. And so why does it happen then if I take sodium chloride and I dissolve it in some water? Why is this spontaneous? We know it's spontaneous from experience. It might be a pain to get it in, but it will go in if you stir in salt and water, up to a point at least. Why does this happen? Well, it can't be enthalpy driven, because we just looked at that. And we know, though, that enthalpy is not the entire picture when we're thinking about thermodynamics. So this, we're going to say, is approximately zero, so we're not worried about it. So what does that mean then? So if we know that this is not the driving force for it to be spontaneous, what must be the driving force? It must be this term over here. I should really look at the whole term. It must be this term over here, T delta S. So entropy is the driving force for dissolving solids in liquids. And this is somewhat intuitive, because if you're struggling, if you want to get, let's say you continue to put salt in water, you get as much dissolved as you possibly can. You could say you saturate it, so you get it to the maximum amount that you can get in. What's a way to get more salt in? You can just heat it up. So increasing the temperature to dissolve things, what you're really doing there is growing this sort of entropy term in the free energy equation so that this number becomes bigger and more negative. Okay? And so, yeah, does it make sense that entropy is the driving force here? It's hard to really look at this and say that from first principles. So I have sodium and chloride, which are solids, and that's going to sodium that's aqueous as well as chloride that's aqueous. That's obviously entropically favorable. And then I have liquid water, so I'm forming bonds. Within that, I'm also forming bonds between the solute and the solvent. And this increases the order within the solution, so that's not a good thing entropically. But it must be that the entropy associated with breaking up the crystal is more beneficial than the entropy associated with forming these bonds within the solution. Otherwise, we wouldn't see the process happening. So the T delta S portion of this drives this, and when we're thinking about what's happening with the entropy, we're thinking about, well, inside of a solid, that's something that's a very low entropy. Sort of system, and then we're increasing that entropy by dissolving it in water. And there is a loss of entropy when we form bonds between the water and the solute, but it must be that those bonds entropically are less unfavorable than the entropy inside of the crystal. And it's not super surprising that that would be the case because, this, even though the sodium is associated with this through weak bonds, it can still move around in solution. It's not like these bonds, the way I'm drawing them makes it seem like it's static, but really it's this system is moving around a whole lot. Sodium is constantly forming and breaking bonds with oxygen. Whereas when I look at sodium chloride in a crystal, actually I can, wait, it's a different page. If I look at sodium chloride in a crystal, there's not a lot of movement that happens in that. These things can kind of vibrate back and forth, but that's about it. So there's a lot lower entropy inside of a crystal than there is inside of a solution, generally speaking. Yeah, what's the other thing here? I guess the other thing to consider is that, like, how will you predict if something's going to dissolve? So the systems we're talking about above with sodium chloride and stuff is sort of it simplifies things, but like it's obviously just based on some of the exceptions I told you about, where delta H can be for solution can be very large in negative or positive. It's not the entire picture. So how can you predict what's going to happen for these cases that are not sort of behaving in this ideal way? There's a little moniker for that, and it's just that like dissolves like. So if I am trying to dissolve something like sodium chloride, which is ionic, so it has permanent dipole moments in it, the solvent, so the solute, let me put it in plain terms first. What like dissolves like means is that the solute IMFs should match the solvent IMFs. Okay, so when I'm looking at, let's say I am looking at, I don't know, like a glucose molecule, and I'm trying to figure out, what it's going to be soluble in. So glucose looks something like, a bunch of carbon atoms. Make sure I get all my hydrogens in here. Oh, that's a mess. Let me draw it in a simplified way. All right, so this is the open chain form of glucose. One thing you'll notice as I draw this molecule out, is it has tons of these OH groups on it. That's really the hallmark of sugars, is they have a lot of OH groups. And these groups, as we learned in one of our previous lessons, are very good at hydrogen bonding. So I got an OH here, 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 I got an OH here. And so when I'm thinking, like, what will glucose dissolve in, it shouldn't surprise us that glucose is extremely soluble inside of water, because, man, these things look a lot alike, and this saying, like dissolves like, is meant to draw your attention between these two things. So this has an OH group, and this has tons of OH groups, and so these things dissolve each other. If we want to get a little bit more sophisticated about it, we could say that this has hydrogen bonds, so it's capable of forming hydrogen bonds, and so does this. These both can form hydrogen bonds. And so when we look at, like, if you're thinking, well, what about like sodium chloride? That's also soluble in water, and it doesn't look anything like it. That is true. Okay, but remember that sodium chloride is ionic, which means that it has dipoles, permanent dipoles. So when it breaks up, right, it's got a big positive charge and a big negative charge. So it's very polarized, you could say. And water is also extremely polar. And so, again, this polarization that we see here with a positive and a negative or whatever. So we've got this positive, this positive. It matches up with these positives here. And then the negative also matches these negatives. And so again, it's this like dissolves like is referring to some extent to the structure. So if they share structural similarities, that it might be true. But more so, it's referring to the intermolecular forces. And so this one has dipoles. And you could say, well, this has hydrogen. This has hydrogen bonds, which necessarily have a dipole component because hydrogen bonds have a dipole component. And this just has dipoles, whereas these have hydrogen bonds that match up to the hydrogen bonds directly. And if this like dissolves like thing is true, then you would predict that glucose would be more soluble in water than sodium chloride is, and your prediction would be correct. And so it just kind of shows the power of this like dissolves like thing. So because the better the solvent and the solute match in terms of their IMFs, the more soluble the solute will be inside of the solvent. Why is that? There's a lot of reasons, but one reason you can think about is that at least in some cases, delta H of solution, which is the delta H of the lattice energy minus delta H of what do we call this? Solvation. This isn't going to change. That's just the energy required, for example, to break apart, let's say, sodium and chloride. So, the lattice energy is like how much energy does it require to separate these two. Delta H of solvation, though, remember, is the delta H associated with forming bonds. So it could be between sodium and like this positive or negative part of the water molecule. So sodium chloride is soluble in water, but it's not soluble in fat. And so, I really want to draw out a full fat molecule. But fat molecules, let me just draw out something that looks somewhat like fat. Let's say like gasoline. So salt, so if you ever cook, try and dissolve some salt in fat. It doesn't work. And the polarity of fat, like olive oil or something, is really similar to the polarity of something like gasoline. So gasoline might have components that look like 1, 2, 3, 4, 5. I don't know. Let's say this in there. If we look at this molecule that I've drawn out over here, what do we say? What do we see? So remember, CH bonds are not polar at all. Even though they're different, we just say they're not polar because the electronegativities are very similar. All right, so what in gasoline or something like it, what are really the only intermolecular forces? The IMFs here are, I forget what we call them. They're van der Waals forces or dispersion forces, temporary dipoles. They have like a bunch of different names. Dispersion forces are like, another word, temporary dipoles is probably a better word because those are just, it actually describes what's going on there. But the IMFs are very weak. They're these weak dispersion forces. This is a non-polar molecule. And over here we have something that is extremely polar. Okay, so if the sodium chloride was hypothetically to dissolve, how would it interact with this molecule we've drawn? It would have to interact through these small temporary dipoles that form on here, and that interaction is going to be incredibly weak, which means that the bonds that form are also going to be very weak. So this bond that might form here between this and whatever, some sort of temporary dipole you could form, very weak. And the weaker the bond, the smaller its contribution is going to be to the delta H. So forming bonds is always going to be exothermic, but in this case, it's going to be very small and exothermic. So delta H solvation, not taking into account, well, no, actually, I think here it's fine. Delta H of solvation is going to be very small in exothermic. Small and exothermic. So if the lattice energy is, even when the delta H of solvation is like favorable when you're dealing with water, if the lattice energy usually wins out and makes it slightly positive, you can imagine that if delta H of solvation is very small, then delta H of lattice energy is really going to swamp it, and thus delta H of solution is going to be extremely large and positive. And if it's extremely large and positive, that means that when we plug it into this delta G equation, it will totally swamp. This will totally swamp the entropy term here. And there's a lot of other things that can come into play here as well that we're not going to get into, but that's just generally how you want to think about things. So if you want to build on those first axiomatic things that we put together, which is that forming bonds is always exothermic, you can add on to that and say, well, the stronger the bond that's formed, the more exothermic it is. And the corollary to that also holds, which is that the stronger the bond is, the more endothermic it's going to be to break it. So strong bonds give out a lot of energy and take a lot of energy to break. Weak bonds put out a small amount of energy when they form, and they also take much less energy to break. Okay? So that's how we think about intermolecular forces and things dissolving when you're looking at a solute and a solvent. The other thing you can think about, the other thing you can think about is just like when you're mixing two solvents, sometimes you'll hear this word miscibility, miscible. And it's the same idea. If I take something like water and I try and mix it with something that it looks like methanol, okay, this can donate, this thing has, this thing has this OH group on it. This also has an OH group on it. They can both donate and accept hydrogen bonds, so they are actually miscible. But as I start to deviate from that, what I'll see is that they become less and less miscible. So if I swap out methanol, which is this molecule, for something like, I'm trying to think of, let's say I swap it out for pentane. This thing has no hydrogen bondings. We just looked at this, a very nonpolar molecule. So this is very polar, this is very nonpolar, and these things end up not mixing together. So miscibility is just it's a different word. So when we're talking about dissolving a solid into a liquid, we're talking about dissolving a solution. We're talking about making a solution of a solid, a solute, I guess, in a solvent. When we're talking about two liquids dissolving in one another, sort of making a solution from two liquids, we refer to that as miscibility. So two solvents will be miscible if they share similar IMFs. I guess the most common one is water and ethanol, which looks a lot like methanol. Methanol is the alcohol that'll make you blind. Sometimes people call it wood alcohol. But these two are completely miscible as well. So like vodka, for example, is a 50%, I think it's around 50% solution of ethanol in water. And Everclear, which is really, really strong, is like, I want to say it's like 95% ethanol in water. So 5% of that is water. Probably makes more sense to call it 5% water and ethanol at that point. But you can put those in any ratio whatsoever. That's what miscibility really is. Okay. I think that's good for solutions. We will skip over Henry's law.